Mathematics is not about numbers, equations, computations, or algorithms. It's about understanding, said by William Howells Trusten. Maths may not teach us how to add love or subtract hate, but it gives us hope that every problem has a solution. Good morning, everyone. We will start our webinar with Tamil Thai Varthu, followed by a prayer song.
நீராறும் கடலொடுத்த நிலமடந்து கெழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழ் எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் மிகுந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
Feedback link will be posted in the chat box at the end of the session. Now, I request Dr. M. Shivagami, Assistant Professor, Department of Mathematics with Computer Application, to deliver welcome speech.
Greetings to one and all. I am Dr. M. Shivagami from Department of Mathematics with Computer Applications, Jayagadas Govardhandas Vaishnav College, Chennai. Thank you for joining us for today's webinar. It is a moment of extreme pleasure to welcome all present here to attend this national level webinar series INFOQUEST organized by Department of Mathematics with Computer Applications, Jayagadas Govardhandas Vaishnav College, Chennai. This event have been impossible without the blessings of the Almighty. I wish the blessings and grace of God be with all of us forever. It gives me tremendous contentment to be presenting the welcome speech among all of you. Before we begin, I would like to express my heartfelt gratitude to our Secretary, Shri Ashok Kumar Mundraji, and our Principal, Dr. S. Santosh Babu, our HOD, Mrs. B. Sankita, and all the faculties of the Department of Mathematics with Computer Applications for their immense support to conduct this event. I'm overwhelmed to welcome our resource person of the day, Dr. A. Tamilchelvi, Assistant Professor, Ramanujam Institute for Advanced Study in Mathematics, University of Madras, Chennai. Thank you so much, ma'am, for accepting our invitation. The schedule of this webinar will focus on the topic of partitions and representation theory. Representation theory is the study of abstract algebraic structures by representing their elements as linear transformation of vector spaces. Roughly speaking, representation theory investigates how algebraic systems can act on vector spaces. Feel free to drop questions on the topic. I wish you all a great, successful webinar. Now, let me invite Mrs. J. Kavita, Assistant Professor, Department of Mathematics with Computer Applications, Jayagadas Govardhandas Vaishnav College, to invite and welcome and introduce the speaker.
Thank you, Sivakami. Good morning to one and all present here. I extend my warm welcome you all to this national level seminar series. This is J. Kavita, Assistant Professor at the Department of Mathematics with the Computer Applications. It gives me immense pleasure to introduce our resource person, Dr. A. Tamilchelvi, who is going to talk to us about partitions and representation theory. Dr. Tamilchelvi is working as an assistant professor at Ramanujan Institute of Advanced Study in Mathematics, University of Madras, Check Park, Chennai. Dr. A. Tamilchelvi graduated from the Valliyammal College for Women, Chennai in 1999 and post-graduated from Meenakshi College for Women, Chennai in 2001. She did MPhil in Pachiyappa's College, Chennai in 2003. She is awarded PhD in 2008 at Ramanujan Institute for Advanced Study in Mathematics, Chennai. She is conferred PDF in Mathematics in 2009 at Institute of Mathematical Sciences, Chennai. She has more than 18 years of experience both in research field and academic. She started her career as a full-time research scholar at Ramanujan Institute for Mathematical Science Study in Mathematics, Chennai in 2002. After completion of PhD, she has joined as a postdoctoral fellow in the Institute of Mathematical Science and joined as an assistant professor in Anna University, MIT campus, Chennai in 2009. At present, she is working as an assistant professor in Ramanujan Institute of Advanced Studies Mathematics from 2014. Her area of interest are combinatorial representation theory, diagram algebras, and then algebraic graph theory. She has published more than 10 articles in reputed journals like Scopus UGC listed journals. She is a member of American Mathematical Society and also acting as a reviewer of mathematical reviews. More than 5 conference and faculty development training programs are organized. She has delivered more than 18 invited talks in various international and national level conference, workshops, and FDP programs. She has participated more than 100 conferences and workshops too. She has two research projects which are from UGC Startup Grant and a DST Purse 2, University of Madras. With this brief introduction, once again, I welcome Dr. A. Tamilselvi to share the valuable thoughts and enhance our young minds. Thank you, ma'am.
Shall we start?
Yes, ma'am, you can start, ma'am.
Thank you for the brief introduction about me and also representation theory. The one who speak about representation theory, she has given the intro. So thank you for inviting me to give the lecture here. So let me start the representation theory and how it is related to partitions. So just a brief introduction. Our goal of studying group representation theory is to study the groups via their actions on the vector spaces. So as she said, it's almost which is related to the linear algebra. The consideration of groups acting on sets leads to such important results as the Sylow's theorem. By studying the actions on vector space instead on groups, we are studying the actions on vector spaces. Even more detailed information about a group can be obtained. So this is nothing but our subject of representation theory. So let me start what is a representation theory. So an action of a group G on a set X, we are going to take a group G. I think everybody knows what is a group.
Ma'am, just
Right?
share your screen, ma'am.
Yeah, it's chat.
No, ma'am.
It's not sharing.
Yes, ma'am.
Is it visible now?
Yes, ma'am. Now it is visible, ma'am.
Yeah, fine. So, as a brief introduction, I'm just starting about the group representation theory. The group representation theory is the study of groups via the action on vector spaces. So, we studied in our PG and UG, we are studying the group acting on the sets, which leads to some important results as Sylow's theorems. So, by studying the actions on vector spaces, even more detailed information about your group can be obtained. So that theory is nothing but our representation theory is. So what's the representation theory? An action of a group G on a set X is by definition it's a homomorphism from G to Sx, where Sx is nothing but our permutation group, symmetry group on X. We are going to give the action of a group to the set. This Sx, this is nothing but X to X. It's just a linear transformation. So we can go with the definition of after this action, we can define the representation. What's the definition of a representation of a group is? A representation of a group is a homomorphism from G to GL of V. This GL of V is nothing but the group of all linear transformation on the finite dimensional vector spaces. So we know what is a vector space and the finite dimensional vector space. So G to GL of V, there is a homomorphism. That is nothing but our representation. This GL of V is nothing but our linear transformation on the vector space V. Right? We are just giving the group acting on this GL of V, this vector space. The action, we are giving the group action on the vector space, which is nothing but our representation here. Representation is representation of a group. So that is what we are doing is we have given the homomorphism from the mapping G to GL of V. The homomorphism is nothing but we have to prove phi of, we have to take for all elements in G, for all G comma H in G, phi of GH is equal to phi of G into phi of H. In the vector space, there is one more property, that is phi of identity is equal to the 1. It is identity in GL of V, right? So the dimension of the vector space is nothing but our degree of the representation. Whatever the vector space we have taken, that is nothing but our degree of this representation is. So we can find the degree using the vector space itself. So we just recall the definitions in the linear algebra. Suppose X is a vector space over the field K, then a linear functional on X is a linear map of the form F is the mapping from X to K. So next, the dual space. The dual space is the vector space over the field K consisting of all linear functionals. What's a linear functional? It is a linear map of the form F is the mapping from X to K, the field, right? So collection of all those things gives a dual space. The dual space is a vector space that consisting of all linear functionals on X. We are going to denote it by X star. So what's the trivial representation is? The trivial representation of a group G is the homomorphism phi, which is a mapping from G to C star. Whether C star is in GL of V, because I said the definition of representation is phi is from G to GL of V, right? Here I am saying G to C star. Yes, it is in GL of V. That is GL1 of V. It's a one-dimensional vector space. We can see this as C star is in GL1 of V, right? One-dimensional vector space. So we can map this phi of G for every element in G. We are going to map everything to identity. Then this mapping is a trivial representation. This is a homomorphism, and whatever we need the condition for the representation is we have to define a mapping from G to GL of V, and the mapping should be homomorphism. Yes, we are through. It is one-dimensional representation, linear transformation. So if phi of G equal to 1 for all G in G is a trivial representation. So next example. Let me take, instead of any G, I am going to take Z2, Z by 2 is Z. Z by 2 is Z. In this, the elements are 0 bar and 1 bar. 0 is nothing but multiples of even numbers, right? 1 bar is nothing but multiple the terms which are of the form odd numbers, right? Phi is the mapping from Z2 to Z star. We are having in this set, we are having only two elements, 0 bar and 1 bar. So given by this phi of m is equal to minus 1 the whole power m. What the element we are taken, we are writing it as minus 1 the whole power that element. So that means it is just a plus or minus 1. This gives the representation. This mapping is a representation. Means it satisfies a homomorphism property. Next, z by 4 is z. Z by 4 is what we can take? It is I power m, right? Since we are in C star, we have to take the I power m. Next, in general, phi of z, phi is a mapping from Zn to C star. This gives the mapping phi of m is equal to the roots of unity, whatever the thing which we are taken, the roots of unity. That is e power 2 pi I by m by n. This is a representation. I'll try to prove this one. So for the identity element is for 0, it's equal to 1. For the remaining elements, we can take phi of r plus s. We can take any two elements in Zn. So phi of r plus s, we can write it as, by the definition, what we are defining in this is e power 2 pi I m by n. M is here, it is r plus s. So we can write r plus s by n is equal to, we can split this into product of e power 2 pi I r by n into e power 2 pi I s by n. This is nothing but our phi of r into phi of s. So now we got the homomorphism property. Phi of 0 is identity and this one is plus phi of r plus s, we are getting phi of r into phi of s. So this is a homomorphism of the vector space. So hence this phi is a representation. Next, equivalence representation. If you have taken two representations, phi is a mapping from G to GL of V and phi is a mapping from G to GL of W, where V and W are vector spaces. These two are said to be equivalent if there exists an isomorphism from V to W such that psi G is equal to T phi G T inverse for all G in G. Then we can say that this phi and psi are equivalent. That is psi G T is equal to T phi G for all G in G. Then we are saying that this phi and psi are equivalent. So we can write in the commutative diagram format also. So V to V, we are having the mapping phi G. So phi of G, we are writing it as phi base G. This is nothing but phi of G. So phi of G is in GL of V. GL of V, GL of V is a linear transformation from V to V. So V to V, same way, the T is a mapping from V to W. We have to take this phi GT is equal to T psi G. So that's what we have to prove. Meaning that either of the two ways of going from the upper left to the lower right corner or the other way, both gives the same. So next example in 2-dimensional, we are seeing in the things, right? So phi is the mapping from Z by NZ to GL2 of C. Till now we are seeing only C star, right? So we are going to see the 2-dimensional. 2-dimensional in the sense 2 by 2 matrices. So phi m is equal to, we can write this as a matrix. The matrix is cos 2 pi m by n minus, what is this matrix? This matrix is nothing but our rotation matrix. A rotation matrix by 2 pi m by n. And psi is the mapping from Zn to GL2 of C. Zn to GL2 of C, we can write the matrix, the identity matrix, like e power 2 pi I m by n and 0 to 0, 0 e power minus 2 pi I m by n. From this, these two, if we are taken phi and psi, we can prove this phi and psi are equivalent. This is simpler, so I'll skip this proof. So one is the standard representation of Sn, because we know if Cayley's theorem says group represents every group is a gives a bijection for the permutation group. We can see every group as a permutation group. So define phi is a mapping from. So I'm going to talk everything about every finite group. We are writing it as a symmetry group, right? Permutation group is nothing but symmetry group. I'm going to talk everything about the symmetry group only. I'm going to give the definition of the example using only symmetric groups. So define phi is a mapping from Sn to GL2 of C on the standard basis. Phi sigma of Ei, we can write this as E sigma of I. Sigma is in Sn. So for n equal to 2, the phi is a mapping from S to GL2 of C. We have, so I'm going to take n equal to 2. That means S to GL2 of C. In S2, we are having only two elements, right? N factorial elements, 2 factorial elements, two elements. That element is one element is identity, the other one is cycle 1, 2, right? So sigma is equal to identity. Then phi sigma of E1 is, we have to take the elementary basis, right? In elementary basis, we are having n dimension is 2, degree is 2, so we can take E1 and E2. Phi sigma of E1 is equal to E1 itself, right? Sigma acting on this E1 will give this E sigma of 1. That means E1 itself, that is E1 is 1, 0, right? So if you are taken phi sigma of E2, that means sigma of 2 you have to see. Sigma of E2 we have to check that. So sigma of E2 is what? 1 goes to 1 and 2 goes to 2 in identity, right? Our identity, sigma is identity. So 2 goes to 2 itself. So E2 we are getting. That means E2 is nothing but the basis 0, 1, elementary basis, right? If you are going for the permutation sigma is equal to this, now we are getting this identity matrix for sigma equal to identity. Next, if you are taken as sigma is equal to 1, 2, then we have to work it out. Phi sigma of E1. Hello, ma'am? Hello, ma'am? Yes? வீடியோவா இல்லை கேமராவா மேம்? வீடியோவா கேமராவா மேம்? ஓகே மேம். Now you are able to see this video on the thing, screen.
Yes, ma'am, we are able to see, ma'am. Thank you, ma'am.
Yeah, fine. Okay. Suppose sigma is equal to 1, 2. Phi sigma of E1 we have to find, and then E2 we have to find it. E1, that means by the definition we have to write E sigma of 1. What is sigma of 1 here? Sigma of 1 is 2 and sigma of 2 is 1 here, right? In the cycle 1, 2, that this cycle 1, 2 says sigma of 1 is 2 and 2 goes to 1, right? So sigma of E sigma of 1, that is nothing but 2. E2, we have to write E2 basis. And then phi sigma of E2, E2 in sigma, E2, this sigma of 2 is nothing but 1. So E1, E sigma of 2, that sigma of 2 is 1. So E1, we have to write this. So this phi sigma mapping, phi 1, 2 is nothing but the 0, 1, 1, 0 matrix. So for the identity, we get identity matrix, and the cycle 1, 2, we get this matrix. That is what we are done here. We are just interchanging the first column or the first row to the second column, first column to the second column, and second column to the first column. That's all. We are just permuting the rows of the identity matrix according to the sigma. We are just changing the rows, or we can say it as a column, right? We are just permuting according to the sigma. This is what the representation of this SN is, defining representation. We are having so many representation of SN. The standard representation is using the elementary basis, we are giving the matrices, and the matrices we are getting whatever the thing is. Just for identity, it's identity matrix, and for all the other permutations, it is according to the permuting how the rows and columns are. So from the above example, what we are seeing is phi sigma of E1 plus E2 plus etc. En equal to E sigma of 1 plus E sigma of 2 etc. E sigma of n, and this is equal to E1 plus E2 plus etc. En. I am not saying that E sigma of 1 is equal to E1. It is any EI. This pi sigma of 1 is any EI and sigma 2 is any EJ. But sum of these numbers, this gives a number, right? So sum of this is commutative. Addition is commutative here. So we can write E1 plus E2 plus En by rearranging that. Because the last equality sigma is a permutation and addition is commutative, we can write this. Okay. So thus the C of E1 plus E2 plus etc. En is invariant under all the phi sigmas with sigma in Sn. We'll go with the definition of what is the invariance of space. Phi is a mapping from G to GL of V is a representation. A subspace W is a subspace of V is G invariant if for all G in G and W in W, the phi G acting on W, it should be in W itself. Then it is G invariant. Right? Next, we'll see what's the definition of direct sum of representations. We are saying standard representation is what, and then invariance of space. Now we are going to see what is the direct sum. The direct sum of representations. We are going to take two representations. Phi 1 is a mapping from G to GL of V1, and phi 2 is a mapping from G to GL of V2. And the direct sum, we can say it's the external direct sum also. The direct sum of the mapping, direct sum of the representation is G to GL of V1 direct sum V2. That is, it's given by phi 1 direct sum phi 2 of V1 V2 is phi 1 of V1 and phi 2 of V2. In the direct sum, the mapping we are writing it as parallel, right? So this is what the definition for the direct sum. Suppose phi 1 and phi 2 are representations, how the matrices will be. The matrix for this direct sum is, it is a block diagonal matrix. We already saw the standard representation of a matrix, right? Standard representation of the matrix. So GLM is nothing but our m by n matrices, m by m invertible matrices over the field of complex numbers. GLN is n by n invertible matrices over the field of complex numbers. Right? If we are direct sum of these two representations, we will get m plus n by m plus n matrices, invertible matrices over the field of complex numbers. These are just a block matrices. This phi G1 is a block matrix, this is a block matrix, and this is a matrix. So we are writing this direct sum as a block of matrices. Direct sum of representations in matrix, it is a block matrix. So defined representations, this 0 is also a matrix. The 0 is a matrix of size according to G1 and G1, phi G1 and phi G2. So defined representations, phi 1 in Zn goes to G star by phi of m is equal to e power 2 pi I by m, 2 pi I m by n, and phi 2 is a mapping from Zn to C star by e power minus 2 pi a m by n, then we can write the direct sum of these two matrices as e power the identity in this element e power 2 pi a m by n 0 0 e power minus 2 pi a m by n, right? Just a block matrix which I said. The block entries are in the diagonals only. So next we'll see what is the irreducible representation is. The irreducible representation is a non-zero representation G to GL of V of a group G is said to be irreducible if the only G invariants of space of V are 0 and V. Then we can say that the representation is irreducible. Any degree 1 representation is irreducible since C has no proper non-zero subspace, right? So it has no proper non-zero subspace. We can say that this degree 1 representation is irreducible. I'm just going to give the link between groups, vector spaces, and the representations. In group, we are studying subgroup. In the vector space, we are studying subspace. That is whatever which is related to the subgroup and subspace in representation theory, we call that the G invariant subspace, which we discussed here now. Simple group. In the group, vector spaces, we are seeing it as a one-dimensional subspace, and in representation theory, we are seeing that as an irreducible representation. In group theory, whatever we have studied, the direct product of groups in vector spaces, direct sum of the vector spaces, and even in representations, we are seeing direct sum of the representations. Group, we have studied the isomorphism theorems, isomorphisms, even in the vector spaces. Here in the representation theory, we are saying that as equivalence class, equivalence representation, right? All these things, all these definitions which I gave it earlier now. So next, if G is just an identity element, it's a trivial group, right? So and phi is a mapping from G to GL of V is a representation. Then what's the matrix? What's the representation we can write it? Phi 1 is just an identity element, identity matrix we can, right? Because we are having only one element in the set, that element we have to map this to I so that it's a group. It forms a group. It follows the homomorphism property. So phi 1 is the only possible thing is identity. So to give you a representation of the trivial group is the same thing as to give a vector space. We have to give a vector. So for the trivial group, a invariant subspace is nothing more than a subspace. The representation of the trivial group is irreducible if and only if it has degree 1. Just now we are seeing. So the middle column in the above table is just a special case of the third column. Middle column is nothing but our linear algebra concept. Now let us see the irreducibility of degree 2 representation. So the representation rho is a mapping from S3 to GL2 of C with basis. I'm going to take the basis as minus V1 minus V2 comma V1 and rho sigma of this is sigma. I'm taken the element in S3. Rho sigma of this Vi is equal to V sigma I, and the matrices are given by rho 1 2 because in S3 we are having 6 elements. The generators are 1 2 and 1 2 3, right? Using these two elements we can write all the others is 4 elements, right? The dimension is 6 3 factorial. We are having the generator and relation, the cycle 1 2 with the cycle 1 2 3 is the generator for S3. In general for Sn, the cycle 1 2 and 1 2 3 etc. up to n is a generator. With that we can write, we can form the group. So this for S3 we are speaking. So row 1 2 and 1 2 3 set, then we can write the remaining elements. For row 1, 2, we can write the matrices as -1 using this basis. Using this basis, I'm just writing the matrices -1, -1, and 0, 1. Same way for row 1, 2, 3, the matrices is of this form. As I discussed earlier, how the matrix will be for the basis. For elementary basis, I am just given. So that I am skipping the steps, how to write this matrices. For elementary basis, I gave for sigma equal to S2, I am taken in that, and I am taken the basis as elementary, E1 and E2. Here I am just given minus V1 minus V2, comma, V1. So for this basis, row 1, 2 is -1, -1, 0, 1, and row 1, 2, 3 is -1, -1, 1, 0. This one is irreducible. From here, we cannot reduce into the one-dimensional case. Why? I'll give the proof for this. Since C2 is equal to 2, order of C2 is 2, right? Plus or minus I. And any non-zero proper S3 invariant subspace is one-dimensional. Let V be a non-zero vector in W. So we can write W as CV. Let sigma in S3. I'm going to take an element in S3. So rho sigma of V is equal to lambda of V for some lambda in C. By S3 invariance of W, we have rho sigma of V is in W. This W is nothing but our CV. So it follows that V is an eigenvector of this rho sigma. V is an eigenvector of this representation with sigma in S3. Right? So our aim is to prove row 1, 2 and row 1, 2, 3 do not have a common eigenvector. So clearly -1 and 1 are the eigenvalues of row 1, 2. We are having the matrix for row 1, 2, right? So row 1, 2 is this matrix. And the eigenvalues for this is -1 and +1. -1 and +1 are the eigenvalues of row 1, 2. And the corresponding eigenvectors are these two, 1, 0 and -1, 2. So clearly, this 1, 0 is not an eigenvector of row 1, 2, 3. Why? Since row 1, 2, 3, 1, 0, we have to apply this 1, 2, this action on 1, 2, 3. We will get the matrix is -1 and 1. Right? Same way, if you are doing it for -1, 2, this is not an eigenvector of row 1, 2, 3. Thus, row 1, 2 and row 1, 2, 3 have no common eigenvector. The above argument implies that rho is irreducible. So what we are seeing in this example, by this idea, we are going to summarize a proposition, that is, we are taken a representation phi of degree 2, then phi is irreducible if and only if there is no common eigenvector for all phi g with g in G. This is what the result we find it from the example. So the next definition of completely reducible. Let G be a group. A representation phi is the mapping from G to GL of V is said to be completely reducible if we can be write it as direct sum of invariant subspaces. Direct sum of invariant subspaces, and this phi is irreducible. Then we can say that phi is completely reducible. This 5 over Vi is irreducible, and we can write V as direct sum of this means we can phi is completely reducible. So equivalently we can say phi is completely reducible if phi can be written as direct sum of irreducible representations. The representation, if a representation is given, then we can write that representation as a direct sum of irreducible representations. This is nothing but our Mashki's theorem. I'll give the statement later. Completely reducible is the analog of diagonalizable in the representation theory. In the linear algebra, we are seeing that as a diagonalizable, and this is now here we are saying that as a completely reducible. In representation theory, we are saying that diagonalization concept in linear algebra, we are calling it as completely reducible in representation theory. So decomposable representation is what? A non-zero representation of a group is decomposable if V equal to V1 direct sum V2 with V1 comma V2 non-zero invariants of spaces. Otherwise, V is indecomposable. It is decomposable means we can write it as direct sum of two non-invariant, not only two, we can write it as a direct sum of invariants of spaces. Then we can say that the representation is decomposable. Otherwise, it is indecomposable. So next, our aim is to show that any representation of a finite group is completely reducible. This was statement of Mackey's theorem, which is important in the representation theory. So to show this, we have to show that any representation is either reducible or decomposable, and then proceed by induction on the degree. So for that, first we have to show that these notions depends only on the equivalence class of representation. That is, phi is the mapping. Phi is the mapping from G to GL of V is equivalent to decomposable representation means. Then we can say this phi is a decomposable. So I'm just given the proof here. Let me skip this now. If the representation is decomposable, then phi is decomposable, we are saying. Same way, the proof as in the previous lemma, we can say that phi is a mapping from G to GL of V is equivalent to an irreducible representation, then phi is irreducible. Also, phi is equivalent to a completely reducible representation means we can say phi is completely reducible. Maschke's theorem says every representation of a finite group is completely reducible. That is, we can write every representation as a direct sum of irreducible representation. Main result in the representation theory is this Maschke's theorem. We can prove using these results. The proof I am going to skip it. So, with this introduction, I'm going to conclude the result in the representation theory is G, let G be a finite group and V can be written as direct sum of the invariants of spaces Mi, Vi, where Vi's are the G invariants of spaces. Then what are the things we have proved? We can prove is the dimension of Vi is this Mi, dimension of this invariance of space is Mi, and then sum of the dimension of this Vi, the invariance of spaces, the whole square is order of the group, whatever the group we are taken, and the number of these Vi's, how many Vi's are there, that number gives the number of conjugacy class of this group. We know how to find the conjugacy class, right? So from that, these two are equivalent. The number of this Vi's, the G invariance of spaces, both are equal. These are the results, these theory results. I'm going to prove all those things using, this is a representation theory result. I'm using the partitions and I'm going to give the results. The number of irreducible representations. This is nothing but this number of VI is nothing but our irreducible representations in the representation theory. Right? So the number of irreducible representations is equals the number of conjugacy classes. So we are just studying, we know what's the conjugacy class in the group. So we can say from that, we can say the number of irreducible representation is this, right? So I'm going to start what is partitions. Before going to the partitions, let us recall the definition of SN. SN is nothing but it's a group of bijections from the set 1 to n to itself, right? So we can write this as a cycle notation. 152746 in S7. So here in this case, 3 is a fixed element, right? So we can omit in the cycle notation. So we can compose two permutations. How we can permute? We can compose using left to right or right to left, but we have to fix one thing. So I am going to use left to right. So 152746 into 134256. This gives using left to right multiplication composition. I am getting this one. If you are doing is right to left, the same pi row, we can do it as right to left also. Then we'll get some other thing. So recall that if G is an element of a group, then the conjugacy class is defined by conjugacy class is it's a set of all x inverse Gx such that x is in G, right? So the conjugacy class for S4 I am given. S4 is symmetric group of with 4 elements. It is nothing but 20. The order is n factorial, so it's 24 elements. So here you can see these are the conjugacy classes. You can see this we are having 5 conjugacy classes. In S4, we are having 5 conjugacy classes. All these things are these conjugacy classes which are related to somehow it is cycle type. The same cycle type have the same is in the same conjugacy class. 1, 2, the cycle type of 2, right? Cycle type 2, 2, 2. So in this 1, 2, 3, 4, 1, 3 to 4, this is 2 plus 2 format. 2 elements in this cycle and 2 elements in this cycle. So 2 plus 2 format. All these cycle types. The cycle types are same in the conjugacy classes. So we are having 5 conjugacy classes in S4. So the conjugacy classes of Sn will be of great interest to us. So we point out that in Sn. 2 elements are conjugate if and only if they have the same cycle type, whatever which I said. That is, for each positive integer, there are same number of cycles of length k in pi and of length k in rho. So, for instance, the elements, these two are in the same conjugacy classes. So, if we insist on ordering our cycles from largest to smallest, then we can associate to each conjugacy class of Sn a partition of n, which is a non-increasing sequence. Lambda is equal to lambda 1, lambda 2, etc., lambda k of non-negative integers, such that the sum of this lambda is equal to n. These things are non-increasing and the sum should be equal to n. Then we can say that lambda is a partition of n. So for this example, the partition is in the first cycle we are having 4, in the second cycle we are having 3 elements. There are 2 elements are fixed, that is 2 and 9 are fixed, which we are not going to write in the cycle type, but in the partition we have to write 1, 1. So this is the partition of 4 plus 3 plus 1 plus 1. This like this, the sequence is 4, 3, 1, 1. The sum should be equal to 9. So this is one of the partition of 9. 4 plus 4, 3, 1, 1 is a partition of 9. So we can associate a diagram for this Young diagram. How we are doing the Young diagram is, let us take lambda is equal to the partition is 5, 3, 2, 1, 1, 1. It's a partition of 12. The sum is 12. So in the first row, we are writing 5 boxes. In the second row, we are writing 3 boxes. Similarly, 2 and 1, 1 boxes. Right? So now what we are seeing, the conjugacy classes of Sn, right? The same cycle type. That gives the bijection with the Young diagrams of Sn. Right? So if lambda is a partition of n, earlier we had discussed number of irreducible representation is nothing but the conjugacy classes. Here we are saying conjugacy class of Sn. I'm particular about Sn. So conjugacy class of Sn gives bijection with the Young diagrams of size n. So if lambda is a partition of n, then we have seen that there is a Young diagram which is associated to that partition. For instance, if we are taken 5, 3, 2, 1, 1, we are writing this Young diagram like this. This is T lambda, I am saying, right? Next, my aim is to write the numbers inside that boxes. So how I am going to write the numbers? I am going to fill the numbers with 1, 2, etc. up to n, right? We can write anything, any numbers in these boxes, then we call it as a tableau. If you are writing the number, that is SR acts naturally on the set of tableau of shape lambda, right? If you are writing the numbers in some format, what is that format? It is increase along across the rows and down the columns. Then we call the tableau as standard. If you are filling just by entries, then we call it as a tableau. If the entries are increasing along the rows and the columns, then we call the tableau as standard tableau. So this tableau is standard. Row wise it is increasing and column wise it is increasing. It should be strictly increased. So to find the number of standard tableau, we are studying the partition. In that we are writing the numbers. In that numbers we are giving the condition that it is strictly increasing along the rows and columns. We can find how many standard tableaus we can use using that. So that's going to define what is a hook length. If AB denotes the box in a row and the column B of the Young diagram of the partition, then the hook length is defined to be the number of boxes directly to the right and directly below AB, including that box AB itself. Right? I'll show with the example. Lambda equal to 5, 3, 2, 1, 1, 1. We are taken T lambda. In that, I'm going to take a box. This is 2, 1, as I given the definition AB. For the hook length of this box 2, 1, we have to add this to the right and also to the bottom, including this box 2, 1. So how many boxes are there? There are 6 boxes, right? So I'm going to fill with that number, 6. To find the number of standard tableau, I'm going to use this definition. Okay, so I'm just filling with the hook lengths. For this box, the number of right is 4 and down is 4, including this box 4 plus 1, it is 9. Similarly, we can fill all the other boxes. So number of boxes in this. So I'm just putting all the hooklets, right? So lambda is a partition of 12. We are able to find this 5 plus 3 plus 2 plus 1 plus 1. It's a partition of 12, and the product of hook lengths 9 into 6 square into 4 square into 3 into 2 square into 1 power 4. This value is nothing but our 7000. This 12 factorial divided by this gives 7700, and that is nothing but our number of standard tableau. That is dimension. Partition is n, right? So n factorial. What's a lambda is a partition of n divided by, I'll give the proper definition. The theorem says if lambda is a partition of n, then the number of standard tableau, I'm writing it as f lambda. F lambda, we can find it as n factorial partition of n. So we are writing n factorial divided by product of that Hij. Hij is nothing but hook length of the node in the ith row and jth column. Right? From this, we are able to find what is the number of standard tableau of this shape lambda. Right? Hence, the dimension of the irreducible representation gives the number of standard tableau. Number of standard tableau is nothing but it is the dimension of the irreducible representation. Number of irreducible representation, we already see that it is the conjugacy class, right? And the dimension of the irreducible representation gives the number of standard tableau of shape lambda. So with this introduction of representation theory and partitions, I'll stop my lecture. If there is any questions, we'll discuss now. Any questions? Pardon, I'm not be able to hear you.
Any questions from the participants? Ma'am, I just have a question. Since I just want to know the basic, is there any research scope based on this hook length and that young shape?
Yes, that's what I'm doing now. So many results are there. So that result only I'm doing. If you need further details, you can come and meet.
Okay, ma'am. Can you refer some papers based to refer this on this topic?
You can see the representation theory book by Bruce Sagan. It's totally basic for the MSc students. Maybe even UG students can read that. Once you read that, you can go with higher representation theory. There are so many books. Even our
Okay,
IMC
ma'am.
faculty
Okay, thank you
has
so much.
given has published a book, and there is a book. So many books are there. Yeah.
Okay, thank you so much, ma'am. Any more questions from other participants?
Yeah.
So, shall we move to vote of thanks, ma'am?
Yes.
Okay. Okay, dear participants, it seems to be a great honor to propose the vote of thanks to all who have helped us in this making this webinar a very resounding success. First of all, I would like to give my hearty gratitude to our distinguished speaker, Dr. A. Shelby, for making an excellent presentation. She has taught the basics of the representation theory and partitions in a very beautiful manner. I would like to express my deep thanks to our secretary, Shri Ashok Kumar Mundraji, our principal, Dr. S. Santosh Babu. I would also thank our HOD, Mrs. B. Sangeeta, for her moral support. I'm happy to express vote of thanks to our faculty members. Finally, I thank all the participants, not only from our department, rather than from all other departments of of other institutions. Thank you so much for your cooperation and for spending time with us. Once again, I thank you all for your cordial cooperation. Thank you, ma'am. Thank you all.
Thank you, ma'am. Shall I leave now?
Ma'am?
Yes, ma'am. Yes, ma'am.
Yeah, ma'am.
Thank
Yeah,
you,
ma'am.
ma'am. Thank you
Yeah.
for
Thank you, ma'am.
Thank you, ma'am.